Hi, welcome to MooMooMath. Today we are going to look at the 3D coordinate system. So we're going to learn how to plot points in 3D. We're going to talk about the distance and the midpoint formula and how we can use that with spheres. Then the last portion, there's a second video on operations, magnitude, and the angle between two vectors. So this is in the vector unit. Okay, here is the three-dimensional coordinate plane. So let me explain how this works. Okay, the x-axis actually goes forward and backwards. So the x-axis runs parallel to a table. It's like a tabletop, front to back. And then left to right is the y-axis. So that goes left to right on a tabletop. Now, this being a three-dimensional, you've got a third dimension, and this is the z-axis, and it is our new third coordinate, and it runs up and down. So as we graph these, the x-axis is forward and backwards, y-axis is left to right, and the z-axis is up and down. And notice that the yellow plane here is called the XY plane because Z is 0. So everything in this yellow plane is just an X and a Y coordinate with Z being 0. The pink plane is called the XZ plane because the Y coordinate is 0. So it would be X 0Y. And the blue plane in the back is the YZ plane where X is 0. So it will just have Y and Z values. Now let's look at what we call octants. Up to now, you've learned the Cartesian coordinate system with 4 quadrants. Well, in 3 dimensions, we double that to 8. So you can kind of see from the drawings all these octants. Okay, the first 4 octants, I always call those upstairs octants. So they are on the top of this coordinate system where the z value is always positive. Okay, the x coordinate, this one's coming forward and right. That's where the first octant is. The second octant is when x is negative and y is moving to the right, so it's positive. So anytime you move forward, like in octant 1, x is positive and y is positive. And of course, z is always positive in these 4 upper quadrants. But in the second one, x is negative, y is positive, and of course z is positive. In the third octant, x is negative because it's going back, y is negative because it's going left, and z is a positive because it's up, so it's negative, negative, positive. And in octant 4, x is positive because it's coming forward, y is negative because it went to the left, and z is positive. So as you can see, these 4 octants are just like a Cartesian coordinate plane, but the third coordinate is z, and the z is always positive. So let me write this first one up here. This is positive, positive, positive. So these are the signs of each of these octants. Now let's go to what I call the downstairs, or the bottom 4. Starting with octant 5. In this set, z is always negative because it's going down. So we can see that x is coming forward, so it's positive. Y is going right, so it's positive. But z is negative, so it's right below octant 1. So the only thing that's going to change is the z coordinate. So this is positive, positive, negative. For the second one, it's just below the second octant. So x is negative, y is positive, and z is negative. So it's negative, positive, negative. And octant 7, x is negative, y is negative, and z is negative. So it's the one octant that is all negative. And the final one, x is coming forward, so x is positive, y is negative, and of course, z is negative. And those are your octants, and those are your signs. And we do want you to be familiar with the octants. So let's try plotting points in 3 dimensions. Okay, here's some examples so you can see them. Like, for example, this one is +2, so this is my x direction, and I'm going to come forward 2. Then it's -3, so I'm going to go left. Now, notice when I go left, I'm going left from this point. So I have to go parallel to the y-axis. And then z is a +3, so I'm going to go up 3. And again, I'm going parallel to this z-axis to then locate this point. So when you're drawing these in 3 dimensions, you can see how the paths are drawn, and you want to draw the paths parallel to the appropriate axis. So let's try a couple. Okay, this first one is -1 to -2. So I'm going to go back on the x-axis 1 unit. Then I'm going to go to the right 2. And notice I'm going parallel to the y-axis, the distance of 2 units. And then I'm going to go down on the z, the distance of this 2 units. I'm going to go down 2. So there is the first point. Now I'm going to call that little a, even though a point should be an uppercase letter. This is a, so I'll label that a. Okay, b, that's a +3. So I'm going to come forward 1, 2, 3. So I'm coming forward 3 on the x-axis. The y-axis, I'm going to the left 1, and I'm going down 1. So it ends up being approximately here. And yes, it looks like it's on the x-axis, but we know we're in 3 dimensions. Okay, let's look at C. We're going to, again, go back 1, but this time I'm going to the left 2. And notice I have to go parallel to the y-axis, and then I'm going to go down 1. Parallel again to the z-axis. So I'll call that C. And then D would be back 3. 1, 2, 3. To the left 2, and then up 1. And that's approximately where D is. Okay, so you can get a sense of how to graph in 3 dimensions, showing the path and staying parallel. Now let's talk about distance in 3 dimensions. Distance in 3 dimensions also, remember, represents magnitude in a vector. So we're going to use this formula to find magnitudes. So let's look at distance in 3D. A 3-dimensional coordinate just has an x value, a y value, and we add a third coordinate, which is a z value. So to find the distance between coordinates, we're going to take these 3D points and use the distance formula. And the distance formula looks exactly like it does in 2 dimensions, but we've added the difference of the z coordinate squared. That's all there is to it. Okay, so let's find the distance between 1, 0, 2, and 2, 4, -3. So the distance is equal to the square root, and I'm going to take my x coordinates and subtract, so 2 minus 1, quantity squared, plus my y coordinates, so 4 minus 0, quantity squared, plus my z coordinates, -3 minus 2, all quantity squared. So that gives me 1 squared, which is 1. 4 minus 0 squared is 16. And -5 squared is 25. So that's going to simplify to the square root of 42. And that is my answer for the distance between 2 points. Now you've got to think about logically kind of what's this going to look like in 3 dimensions. So I'm just going to do a quick sketch over here. So I've got 1, 0, 2, point right here parallel to the z-axis. And then the next one is 2, 4. So I'm going to the right 4 and then down 3. So here, in 3 dimensions, I'm trying to find that distance, and that's the square root of 42. So that's kind of the visual that goes with it. Okay, so let's talk about the midpoint in space. The midpoint in space looks exactly like the midpoint in 2 dimensions, only we're adding the third coordinate, which is z. So remember midpoint, you add the x's, divide by 2, add the y's, divide by 2, and add the z's and divide by 2. So let's find the midpoint between the point 5, -2, 3, and 0, 4, 4. So for the x coordinate, you're going to add the x's, divide by 2, y, add the y's, divide by 2, and add the z coordinate, and divide by 2. So here is the setup to solve. So it's going to give me 5 halves, which is 2.5. This is going to give me 2 divided by 2 is 1. And the last one is just 7 halves. And that would be the midpoint between these 2 points. It's very simple, just like the midpoint formula, only adding the third coordinate. Now let's look at how we can apply the distance in the midpoint, because we're going to deal with a sphere. So just like a circle, we are just going to add that third set of variables to create a sphere. So the equation for a sphere in standard form is x minus h quantity squared plus y minus k quantity squared plus z minus j quantity squared is equal to the radius squared. So you can see a little picture here where h, k, and j is the center of the sphere. And every x, y, z is a point on the sphere where r is our radius. So we've got a center, a radius, and then a point on the curve. So let's look at the similarities between the circle equation and a sphere equation. So a sphere equation, a circle equation, the x's are the same, the y's are the same. The only thing we're adding is the z's. Okay, so as it's true with the equation of a circle, the equation of a sphere is simplified when it's, so we have this very simple equation if the center is the origin. So if h, k, and j are all 0, it's just going to be x squared plus y squared plus z squared is equal to r squared. So that's where the center is at the origin. Okay, so now let's write the equation for a sphere that has points 6, 1, 0 and 0, 1, 8 as endpoints of a diameter. So you can think of this in 2 dimensions if you want to. So think about the fact that, okay, you'd have 2 points that are the ends of the diameter. How would I write the equation of a circle? Well, I need 2 things. I need a center and I need a radius. Same thing happens with a sphere. We need a center and we need a radius. So the first thing I'm going to do is find the center. Well, how do you find the center between the endpoints of a diameter? Well, think about a circle and the endpoints of a diameter. I need the middle, so I need to use my midpoint formula. So to find the center, I'm going to take 6 plus 0 divided by 2, 1 plus 1 divided by 2, and 0 plus 8 divided by 2. And so my center ends up being 3, 1, 4. So there's the center of my sphere. Now I need to find the radius. So at this point, I can find the radius by finding the distance from the center to either endpoint. So I'm just going to pick this endpoint. So let's find the distance from the center to one of the endpoints. So the distance formula is simply, what's that, 6 minus 3. So 6 minus 3 squared plus 1 minus 1 squared plus 0 minus 4 squared. And there's my distance formula in 3 dimensions. And that gives me 3 squared, which is 9. That's the square root of all this. 1 minus 1 squared is 0. And negative 4 squared is 16. So this is going to equal the square root of 25, which is just simply 5. So there's my radius. Now we just need to plug into the equation of a sphere. Well, the equation of the sphere is x minus h squared plus y minus k squared plus the third dimension, which is z minus j squared, is equal to r squared. So let's plug in our center. So let's go back up. We got the center of 3, 1, 4. That's my HKJ. So let's plug in x minus 3 squared plus, it was 1, yeah. Y minus 1 squared plus z minus 4 squared is equal to the radius squared. Well, our radius was 5. Our radius squared then would be 25. And that would be the equation of the sphere. So we had to use distance and midpoint to find that position to describe a sphere. Now, let's say we have a sphere, but it's not in standard form. What do we do to convert it to standard form so we can then identify the center, the radius, and then graph it? So what we have to do is we have to complete the square just like we did in conics, but we have to include a third variable z. So the first thing we want to do is group our variables together. So I'm going to group my x's first. So x squared and 4x, I'm going to put that first, and I'm going to leave a space so I can complete the square. And then my y squared, I'm going to bring down my negative 2y with it. Then I have a z squared, so leave a little space for completing the square. And then z squared, and then I have a positive 8z. And then I'm going to move my constant to the other side. So as I complete the square, I add my constants to the right. Now let's complete the square. So you have 4 and you square it, so we're going to add a 4 to complete the square. So let's add 4 to both sides. Half of 2 is 1, 1 squared is 1, so we're going to add 1 to both sides. Half of 8 is 4, 4 squared is 16, so we're going to add 16 to both sides. And so we've completed the square by halving and squaring and adding to both sides. Then we're going to factor our trinomials we created. So this is x plus 2 quantity squared plus, let's look at the y. The y is y minus 1 quantity squared. And the z is z plus 4 quantity squared. So we factored each set of trinomials. Now on the right, I've got a constant. Let's say that's going to give me a positive 21 minus 10. So that's 11. Right? Does that look right? Yeah. Okay. So now I can identify my center. My center is always x minus h. So that's going to be a negative 2 for the x coordinate. Y minus k, so k is just positive 1. And z minus j, so that's going to be a negative 4. So I now have my center. That's the center of my sphere. And then my radius would be the square root of 11, because this is equal to r squared. So it would be the square root of 11. So now I can graph that if I want to in space. where you'd have to estimate, right, the square root of 11, which is a little bit bigger than 3, smaller than 4, so maybe like a 3.3-ish is what you'd have to graph that to be. So there you go, and that's how you find the center and the radius of a sphere given a sphere not in standard form. So let's do one more application of the distance formula. Okay, let's say that we want to find the distance or the length of the diagonal. Well, up to now, we've only been working in 2 dimensions. So what you can do is take the flat surface of the base of this cube that measures 4 by 4 by 4 and find the length of the diagonal using the Pythagorean theorem. Then you can use that answer with a height of 4 to then find the diagonal in 3 dimensions. Well, you no longer have to do that. You now can find this distance using a 3D system. So for example, if we think of this as being the origin of a 3-dimensional system, where this is your x-axis, this is your y-axis, and this is your z-axis. You can now find the length to this point. Well, what would that point be? Well, that would be negative 4, negative 4, negative 4, positive 4. So negative 4, negative 4, and positive 4. And I'm finding the distance from the origin to this position. Well, what are the coordinates for the origin? 0, 0, 0. So really, I just need to find that distance. So the distance would be the square root of 4 minus 0 squared plus 4 minus 0 squared plus 4 minus 0 squared. So that's going to give me 16 plus 16 plus 16. So what's the square root of 48? Well, that's just 3 times 16. So that's just going to be 4 square roots of 3. There we go. And that would be the distance of the diagonal. So hopefully you see a little pattern. I do this often in class where we know a 45, 45, 90 triangle. If you have 4, 4, this is 4 square root 2. That would be the hypotenuse. And not just because you're adding a 3rd dimension. Notice the square root becomes the square root of 3 because you have 3 16ths. Anyway, just a little thing to make it simple for you if you're dealing with a cube. So that is kind of the basics of the 3D system. And the next video is going to be on operations in vectors, with vectors in space in 3 dimensions. So you can watch that other video, but this is the first one, just getting your feet wet with the 3D system.